Flight attendant, I know you have a choice in which presentations you can come and see. Thank you for choosing me. So, who am I? Here's a little bit of information about me. So, I'm Chris Roebuck. I started out my career as a physicist at a government research laboratory. I spent a number of years doing RF test and measurement. I've been a LabVIEW user for 22 years. I was reminded of that the other day, 22 years. So, disclaimer, I'm an old timer. You will not see any quick, sorry, is Darren here? No, good. You will not see any quick drop shortcuts. You will not see any right-click plugins. You will see liberal use of tab, spacebar, and me fumbling to find things in the palettes. I spent 22 years learning where the colour box constant is. Heck, I'm not going to give up the palettes just yet. I've been a TestStand user since TestStand 3, so kind of probably 15 years ago now. And I'm still recovering from a series of misguided attempts to build my own test sequencer. And I'm a huge LabVIEW geek. I think I'm actually the only person in the UK to hold that certified LabVIEW geek accreditation. That was a birthday cake, by the way. So I'm a software architect at Delacorp. We're a multinational NI Alliance partner. We've got Fabiola de la Cueva and Luis Rosco here in Austin. And we also have an office in Europe. Guess which one I work for? So what we do at Delacorp, we do software design and implementation. Really, we work with teams who already have LabVIEW developers. We work with existing development teams and implement processes, source code control, reuse library, style guides, setting up custom V-analyzer tests, that kind of thing. We do a little bit of integration and turnkey solution, but not so much. I in particular look at automated test strategy. So understanding how people can use TestStand for automated test and reuse those automated tests in the best way. We do some best practice training, a little bit of hardware design, and my pet kind of specialist subject is test data management. So how we handle the test data that our ATE systems produce and how we can do that analysis. So here's the agenda. It's a little bit of a story rather than agenda. It describes certainly a journey that I went on, and I'm sure that many of you will be familiar with this journey as I go through the slides today. But it starts with LabVIEW. And I talk about how we often find ourselves rolling our own test sequencer. I'm going to introduce TestStand, show how we discover TestStand, some of the mistakes that newcomers to TestStand can get into, and how you can fix that. And I'm going to propose an architecture of how we can do our TestStand development as a LabVIEW. So where do we start? Well, certainly my story was that I was asked to automate. I was working at a government research laboratory, and I was asked to automate a lab. I think it's fair to say that the lab I was working at, they didn't have a tidy desk policy. And the lab manager basically, he came to me and he said, we need to do some automation. So a little bit of background, the project that I was working on, I was measuring the metal content of some pots that had been dug up in ancient Greece. And they didn't want to destroy these pots, they just wanted to measure the metal content. So we were going to do some impedance measurements. So the lab manager, he gave me this impedance analyzer, and he gave me two boxes. He gave me Borland C++ 4.5, and he gave me LabVIEW 3. And the instruction was, make one of those, do something with that. So I tried C++, and then on the following day I opened the LabVIEW manuals, and I started to do some LabVIEW code to automate that kind of setup. And as I say there, it all starts with LabVIEW. Kind of the 3 VI solution. Yeah, I know there's 7 VIs up there. That was the driver that I picked for this slide, but we're kind of familiar with the 3 VI solution of open, measure, close when we're programming instruments, for example, or I think NI call it acquire, analyze, and present. But that kind of model that we're familiar with. And we have some benchtop automation. So there, I'm just programming a power meter to take a power factor measurement. So we're controlling an instrument and returning a value from the instrument. We're familiar with that. But measurements can quickly become tests. So now we're applying some limits, some limit checking to the value that's being returned. So our benchtop measurement has become a test. And I've got some high and low limits that I can apply to that measurement. let's add some result storage. So the manager comes along and says, yeah, I need to see these results. I want to send them to a customer, or I want to put them in my report. So we add some storage. So there I've just got some write to file primitives, but it might be database storage. We might be writing to Microsoft Excel, for example. Then the manager comes along and says, can we add another test? Okay, yep, I can add another test, and the API for this instrument's a little bit more complex, so we've got a few more VIs. It's not quite the 3 VI solution that I talked about. Oh, and now I've got 3 sets of limits to, 3 sets of test criteria to worry about, and all of a sudden my file's getting a little bit more complex too. Then we discover LabVIEW is amazing. We start using things like object-oriented LabVIEW, where we can abstract the hardware away from our test solution. We can start plugging in different models of instruments, or plugging in different tests. So in this particular code, I've got a loop running, and at runtime, I'm using dynamic dispatch to call different tests. So these plugins allow me to do selective sequencing. At runtime, I can choose to perform different tests. So we've rolled our own test sequencer. We can now apply limits to measurements and obtain a result, write to file, and we can programmatically choose which measurements we want to perform. And as an independent consultant, I see this a lot with companies where they've built their own test executive effectively. And where that can become problematic is that it requires not only specific knowledge of the problem that you're trying to solve, it requires specific knowledge of the solution that you've arrived upon in order to solve that problem. They can quickly become unwieldy and hard to maintain. People do leave companies and they take with them that specialist knowledge. And often they use proprietary sequencing. So we've all come across, how do you decide which test to run? Well, there's some magic spreadsheet where you have to put a yes in a particular column, and that determines whether the test runs or not. But is it uppercase yes or is it lowercase yes? Who knows? The guy left last year. So we get the proprietary sequencing, Excel, directories, XML maybe. I've seen a variety of different things. And there's no external support network. When you've got your test suite sequencer and you've got a problem, you can go on the LabVIEW forum, maybe show some code, but they're not aware of your solution. They don't know it in detail. You ring up NI, they'll say, can you send me the whole thing? Yeah, I'll send you a gigabyte of LabVIEW files. So it can be difficult to get support. So we've all met this guy, right? The guy that rolled his own test sequencer based on Excel. I've met this guy many times. And we've been in this situation as well, where we've got this behemoth LabVIEW application that performs all of our company's testing. And I changed one thing. I added a line to Excel, changed one VI, and the whole thing stopped working. Didn't change anything. Why is it not working? And then our friendly National Instruments representative comes along and he sees what we've done, and when he's recovered from the heart attack, he said, well, we should try TestStand. So we try TestStand. Now, one thing I found with kind of my experience in the field and meeting different companies and different organizations as a consultant, there's a lot of misconceptions that surround TestStand. The first one is, it's just an off-the-shelf sequencer. It just sequences. My LabVIEW code sequences tests. Why do I need this thing? Well, it's not. It's a test framework. It does an awful lot more than sequencing. It certainly can provide sequencing, but it provides decision-making logic. We can decide to run one test or another test. We can repeat tests if perhaps the results were unfavorable. The next misconception is it's rigid and inflexible. Actually, I really want to. It used to ship with a poster that is like the size of this screen, detailing the whole API of TestStand. I couldn't get hold of one for today, unfortunately. They now supply on a PDF as it costly to produce that. But it's very flexible. If anything, it's too flexible in what it can do. And I've seen solutions where people have turned TestStand almost into a programming language of itself. And the last thing I hear is, I don't need TestStand. It's overkill. I don't need TestStand for. It does user management. It produces reports. It can repeat tests and make all this decision making. It can test multiple DU2s at any one time. Well, we end up implementing that stuff anyway. We end up saying, well, if the user's an operator, let's give them this menu. If the user's an engineer, let's give them a different menu. Let's do different reports. Or another customer comes on, they don't want their Excel reports, they want HTML reports. So we end up implementing that stuff anyway. that repeats, skip a repeat test, skip pass if the previous one failed, that kind of stuff. We end up implementing it anyway. But I do find that TestStand is extremely misunderstood. I tried to find a good picture that showed misunderstood. I found this one. I really like this. So, what is the outcome then? So they buy TestStand, and they've got their library of LabVIEW code, this huge library of LabVIEW tests that they've written over the years, and they buy TestStand and they open it up and they write their first test sequence, and they end up with what I call the VI. Okay. So what does the VI look like? So here I've got an existing LabVIEW test, and it's got a video running. Okay. TestStand. He's got his test already. He launches TestStand and opens a brand new sequence, logs it, because TestStand provides user management, the thing that they didn't want, and they add a single step into TestStand. They add a pass-fail step, for example, and they add the entirety of the code that they just wrote. So, let's save the sequence, run TestStand. It's going to ask me for the serial number again, something else that they didn't want and that was overkill. They output the pass-fail result of that LabVIEW step and return it to TestStand as the overall result of that pass-fail. Save the sequence. And then execute the test. So the first thing TestStand's going to do is ask me for the serial number, the device under test, and hit OK. And TestStand kind of seems to do nothing. It just sits there. So that nice previous view that I had of the temperature adjustment of my device under test, it's hidden because TestStand, it's not respecting the modality of that window. It's not bringing it to the foreground. I've got to do a little bit of work if I want to do that, and then I get the complaint, well, I didn't see what was happening. I've lost all the information. I can't see what's happening at any one time. But they got some benefits. They got a nice report. So I see that an awful lot where a customer has written a large LabVIEW-based test and then have just imported it wholesale into TestStand to just return a single pass-fail result. So the issues with that: no user interaction or information about the progress of the test. They don't get to see the outcome of supporting steps. So they don't know whether the temperature was achieved or not. They never got to see that. Debugging is far from granular. They're still having to go back into LabVIEW to debug the entire thing. The benefits, well, they got results handling for free. Get some pretty nice HTML reports out of TestStand. And it's an easy win. Yay, I implemented TestStand. Great, took me 5 minutes. The other outcome that we sometimes see is they discover pretty quickly after that first example, they discover that TestStand is amazing as well. What does that look like? Well, in this particular example, I've got two LabVIEW libraries here on the left-hand side. I'm sorry, the resolution's a bit poor. We've got two LabVIEW libraries. We've got a spectrum analyzer instrument library and a power supply instrument library. And in each of these libraries, we've implemented some methods. So for the power supply, those methods might be something like set current, set voltage level, set output state, or return a current measurement from the instrument. The spectrum analyzer also implements some methods. Then, those library methods are being called from TestStand. So let's take a look at one of those test sequences. I think we're going to go in and have a look at the power on DUT, for example. So we've got some test sequences on the right-hand side. And because we're making calls directly into a LabVIEW instrument driver, TestStand now has to be aware of those references. So we're now having to hold those references as parameters, station globals, however we decide to do that, but TestStand needs to be aware of those references now. So we're making calls on the public API, on the API of our instrument driver from TestStand directly, but on each one we're having to pass in and out the reference to that particular instrument so that TestStand can communicate with it. And we've got, as you saw in that previous sequence, we have 10 steps just to configure our power supply. And that's 10 opportunities to miswire or to incorrectly pass the reference from one API call to another. So you can see we've got a lot of granularity there. Some of the issues that we get with that are that there might be preconditions that are needed for some of our test sequences. So perhaps we want to perform one of the tests that we've got on the right. So we've got a linearity test, a phase noise test, and the other one's a spurious emissions test. Let's say I just want to run the spurious emissions test. Well, unfortunately, the device needs to be powered up in order to do that. So now I've got a precondition, a dependency, a precondition to power up the device on the test first. I can't just run the spurious emissions test. So I've got these dependencies now within my test sequence. What happens if I just want to run the single test? Maybe I could TestStand allows you to select multiple steps to run, so I can do that. But unfortunately, unless somebody wants to correct me with the latest version of TestStand, you can't cross step groups by selecting steps and then saying execute the selected steps. So I've got to find some way of programmatically deciding. So that in this instance, I've put some Boolean preconditions around each test, and then I've had to write a little LabVIEW UI that pops up and says, which one do you want to run? So I'm now having to cope with the fact that I've got what I'd term excessive granularity in my TestStand sequence. So TestStand is amazing, but it can result in an overly granular TestStand sequence. Last year I visited a customer and they were telling me that they were having some issues with TestStand, and I opened one of their test sequences and it had over 900 discrete steps in a single sequence. That's a lot of individual steps. Every single one of those steps appears in the test report or has to be deselected so that it doesn't appear. Now there's some neat features in TestStand now where you can actually select a group of things and apply a common property to them all, like deselect. That wasn't in TestStand 3.5, which is the version they were using, so some person had gone through and actually manually edited 900 steps. So the issues, if we take that course of action, references, handling, references need to be carefully handled. If we're going to deal with the references at the TestStand level, we need to be a little bit careful. Everything goes in the report. That could be a positive or a negative. 900 steps, that's a lot of steps to not appear in the report. And there are certain situations where we can't run or test individual steps, or running them individually might not provide a meaningful result. Often preconditions are taken for granted. The benefits, it's really easy to observe progress. As our test is running, we can see exactly what's happening. Just as we can when we run it from LabVIEW in its entirety, if we take this course of action, we can see how the test is progressing. And it's easy to reuse sequences on other projects. Well, really, both of those two situations are undesirable. We've got this disconnect. Some of the problems that we might encounter are, how do I just test part of the sequence? Just want to run one of the tests. How do I do that? Which environment is best for debugging? This is a really interesting one, and you'll get different answers depending on who you talk to. But really, personally, I find the LabVIEW environment is very good for debugging. If I've got 900 steps in my TestStand sequence, I'm constantly hopping in and out of LabVIEW and TestStand, back to TestStand, back to LabVIEW. It can become a little bit of a debugging nightmare. How do I test without hardware? So now I've got this situation where I've changed my hardware set, or I don't actually have a piece of hardware present, so somehow I've got to have simulation code in there. So TestStand does support object-oriented LabVIEW, so I could implement something like that. But then that's 900 steps potentially that I've got to go back and re-edit and make calls on a generic class rather than a specific class, and that can all get a little tricky. If you're using older versions of LabVIEW, then you don't TestStand, then you don't have that option because there wasn't support for older versions. Chris, remind me, what version? 4.2? 4.2, yeah. So if you're using older versions of TestStand than 4.2, you don't have that opportunity. How do I deploy? So if I've got a single test, then I've probably got a library or a source distribution or something like that, and a single TestStand sequence. So maybe deployment's not going to be the issue. But if I've got a highly granular test system with maybe different plugins, different classes that might get loaded at runtime, then I've potentially got to supply everything that's required. So deployment can become a real consideration. And how do I patch and upgrade? This was a question from a customer recently, actually. They really wanted a strategy for, I've got a TestStand solution in the field, and I want to push out just a driver level update or a sequence level update without updating the driver. So we need some kind of strategy, depending on which two setups we've gone for. We need a strategy to be able to upgrade and patch. And then the really important question, does this mean I now need a TestStand architect and a LabVIEW architect on my team? And that could be expensive. It's good for some people, right? Maybe not for us. So is there another way? So I'm going to talk a little bit about a project now and how I discovered a different way of programming TestStand and LabVIEW together. So a little bit of background. Sorry, it's a little bit bullet point heavy this part, but it was 2010, and I had a project to test a reaction wheel for the space industry. This is basically, it's a brass wheel, probably 8 inches across, and it spins really, really fast. And if you put 3 of them on a spacecraft in X, Y, and Z plane, and you spin them in a particular way, you can affect a turning moment on the spacecraft to make sure the spacecraft is constantly pointing at the point on Earth that you want it to point at. So we needed a way to test these things in a kind of a closed loop system. They have some feedback by measuring the Earth's magnetic field. So we wanted a test system for these things. We wanted to communicate, the requirements were we wanted to communicate with potentially 3 wheels, and there is some interaction between them as well, but we wanted to communicate with 3 devices in the test. We needed to control some data acquisition, and we had a single data logger collecting information from 3 reaction wheels, and they were powered by a single DC power supply because the customer was cheap and didn't want to power them individually, so they just bought a big one and hooked them off. We also had a thermal chamber, and we needed to be able to control the thermal chamber and have 3 devices under test, 3 wheels in the chamber, and cycle them over temperature as well. So that was the kind of the specifics of the test. From a project level, they wanted these kind of high-level requirements. They wanted a functional test. They wanted to be able to hit the go button and have a pass-fail result for each wheel that was being tested. So it's kind of a high-level requirement. They wanted to do continuous monitoring. This is the space industry, and the customer can ask at any point, show me the entire history for when the device was powered, even if it wasn't a functional test. Maybe it was some debug or some engineering evaluation type work. They want to know about everything. So there has to be continuous monitoring of the device under test throughout its test campaign. Multiple unit testing, they want to be able to test 3 at any one time, sometimes 1, sometimes 2, sometimes 3. And they also wanted interactive diagnostic control. An engineer wanted to come in and be able to spin up a wheel and measure some parameters, but maybe not perform an actual test. So, at the same time that requirement landed on my desk, I was at the CLA Summit here in Austin, 2011, and there was a presentation by Justin Goss. Sorry, hands up. Anybody here for CLA? Okay. CLD? Okay, this is a reason, if you're a CLD, this is a reason to maybe get your CLA. Very valuable event, free event. You just need to get yourself to Austin, or they have an event in Europe as well, if you're European. Absolutely, definitely worth getting a CLA and attending. So, CLA Summit presentation by Justin Goss, who was at JK at the time. He gave a presentation on something called the Private and Public Events Framework, a way of having well, let's talk about it. What is a private event? So, basically, a private event, that's a really old screenshot. A private event is a wrapper around a VI that fires an event. So we've got a library here, and we've got some public wrappers around private events. So some of the API methods are private, and then if we want to expose them to people outside of the library, we wrap them in a publicly scoped VI. So that kind of resonated with me at the time, because I was starting to think, well, in the case of my test system, my power supply is a module. It's got methods, set current, set voltage, set the output state, but it's an entity on its own. And it might be that a test sequence is trying to communicate with it, but it might be one of these diagnostic or interactive tests is trying to communicate with it. So it struck me that that was an entity on its own, as was the device under test itself. It has methods like set speed, set direction. So this private events concept kind of resonated with me, and I later found out that it's part of this concept of actor-oriented programming, where we have a module, something, a device under test, an instrument, we have a module, it has something. It has private data, information that is held by itself. It has a public API, and we use messages to interact with the data within that module, to interact with the module itself. So we have inbound messages, and we call them requests. We're asking the module to do something. In the case of the power supply, set your output state to true, set the current limit to 0.5 amp. And we have broadcasts, outbound messages, where the module is saying, hey, I did something. I tripped, or I did set the output state. So we've got inbound and outbound messages into a module. And this module exists and has, what does the module have? It has statefulness, it has private data that is private to the module. It has a public API to allow us to interact with that data and to invoke methods on that module. It has no knowledge of who's consuming any of the data that's broadcast. It doesn't care, it shouldn't care. It's saying, I did something. So that gives us a little bit of an overview of a module. Private data, public API, and we use messages to interact with it. So in the case of my situation, if I take the power supply, for example, it's got properties that are held within its private data. Those properties might be the instrument's name and its visa reference. And it's got some very simple methods. The thing the module can do, the thing the instrument can do. So set the visa reference, set voltage, set current limit, get current, set output state. So then my module looks kind of like this. I've got some private data that holds the visa reference. I've got a public API, things that I can do, things that I can invoke upon the module, and I use methods to interact with it. So I can then program that API from LabVIEW. So here, I'm interacting with a module. In this case, I'm interacting with the thermal chamber that I showed you earlier. So here, I'm making API calls on my thermal chamber. So in this particular instance, I'm setting a ramp rate, I'm setting a set point, and I'm waiting, I'm requesting it to do those things, and then the module is sending me its actual temperature back as a broadcast. That's my API for my module called from LabVIEW. The module's running asynchronously to this block diagram. So here I'm launching the module, waiting for it to start, and then I'm interacting with it. It's running asynchronously to this block diagram. And the API is fairly clean, fairly simple. I can then call that exact same API from TestStand, because if you notice, in the previous block diagram, there were no references. The only thing I'm passing in and out of those VIs is an error cluster in order to enforce the sequence of those operations. There's no references that are holding on to that. So I can then do that from TestStand as well, making calls on the exact same API VIs. So in this case, I've got a little bit of setting up of TestStand parameters up at the front, but then I'm calling the exact same VIs. So show the thermal chamber front panel, update the set point, and then request in return the status. Tell me what your status is, tell me what your temperature is. And I'm doing that until it reaches the target set point, and then I'm closing the thing down. I'm doing exactly the same as I am with that LabVIEW VI. So, just to recap, in terms of integration in TestStand, TestStand sequence, sending messages to our module, our continuous monitoring, our power supply, our device under test, and each one of these APIs effectively is just sending one of these private events, a user event, to our module. Effectively gives us a very thin
TestStand layer where all we're doing in TestStand is making calls to an API. Therefore, our end application has a particular client. That could be a LabVIEW application, it could be a TestStand sequence, and running asynchronously to this application would be several modules. In this particular example that I was talking about, we had the actual device under test control, so that was controlling the momentum wheel, controlling things such as its speed, its torque, and the change in speed, or the rate of change in speed. In addition to that, we had some continuous monitoring, so some data acquisition that was going on, that was capturing temperature data from various points around the momentum wheel to make sure that we weren't driving the motor too hard, monitoring some currents, some voltages at various test points on the control board of the wheel. We also had, running asynchronously to our TestStand sequence, we had a DC power supply module where we were able to send commands to set the voltage level, the supply current, the power on state, and the over voltage protection trip level. This allowed us to perform tests where we would drive the wheel and then would see what the behavior was if we took the supply voltage below a minimum threshold or overdrove the supply voltage. And then we had a final module which was running asynchronously, and that was our thermal chamber controller. So this device, this wheel, sat within a thermal chamber, and we would perform the various tests on this wheel, things like stiction, friction, etc. Those tests would be governed by the sequence of operations in the TestStand sequence, and upon completion of a test, we would then perform some kind of temperature adjustment. So we did the typical hot, cold, and ambient temperature profile, but we might also perform some of the tests as we were making those temperature transitions to see how the behavior would change over temperature. So how did that work out for us then? Well, I think immediately some benefits were recognised, and hopefully you've seen some of those, in that this allows you to debug your API entirely in LabVIEW. You can create a module that has public events that you can fire from either another LabVIEW application or from TestStand, but it allows us to debug that API entirely from within the LabVIEW environment using our API tester. Certainly, my preference is to perform my debugging in LabVIEW. There are a lot of tools that I've grown accustomed to use when debugging VIs, and personally, I find it much easier to do my debugging in a single environment rather than trying to co-debug, if you will, by stepping through steps of a TestStand sequence and then stepping into a VI where I can monitor its behavior, then stepping back out to the TestStand sequence. I find that hopping between the environments isn't conducive to rapid debugging. So one benefit is being able to debug the API entirely in LabVIEW and effectively know that you have a solid interface and that the module is behaving as it should when you then go to make your calls from TestStand. So we also have the ability to call the API from LabVIEW and or TestStand, and we can interact with it from both at the same time. These are just public events that are available to be fired from any environment which has registered to either hear about them or make calls on the public API. This means that we can run our TestStand sequence, and in parallel to running our TestStand sequence, we can register to hear about certain events in another LabVIEW VI, or we can even inject events from another LabVIEW VI, and this can greatly aid in debugging, where we can introduce error conditions or maybe set corner case values, edge case values, and monitor how our TestStand sequence behaves or how our module behaves under those corner cases. So this is extremely powerful, being able to call the API from LabVIEW and or TestStand. Ultimately, this results in a very thin TestStand sequences. So previously, where we had references being passed around the TestStand sequence, being held within parameters, local variables, station global variables within TestStand, those references are now held internally to the module in the module private data. This results in a very thin TestStand sequence where all we're doing is making calls to the public API from TestStand. But like all these things, no such thing as a free lunch, so we found some issues. One of the first issues we found, and this really was unexpected. I guess it shouldn't have been. There's a line in the LabVIEW help that refers to this specifically, and that is the issue around user event lifetime. So suffice to say that a user event reference has an owner. It turns out that the owner of that reference is the block diagram or the hierarchy of the block diagram in which that user event was created. So, and the lifetime of the event reference is then bound to the lifetime of that VI. If that VI no longer is executing and is no longer in memory, then that reference is effectively deemed to be no longer required. LabVIEW says, look, you created it in this VI, that VI is no longer running, therefore, that reference, I can safely tidy it up. That might not be the case, but that's what LabVIEW does. So the reference goes bad. So that's the key point. The reference is owned by the block diagram hierarchy upon which it was created. So imagine the situation where we have a TestStand sequence that launches an asynchronously running module, and as part of that launching process, the VI that performs that launching creates some user events, defines some user events, creates them, and passes those references to the module. When that VI stops executing, those references go bad. Even if those references are held in some kind of variable or uninitialized shift register, perhaps in a functional global variable, which is a common way of handling this, then those references still go bad. Even though they're still in memory, being held in memory by the FGV, they go bad because the original block diagram upon which they were created is no longer running. So imagine the situation where in TestStand you have a single VI that's launching the module, creating the user events, the module's then launched, it's running asynchronously. As soon as TestStand stops executing that step and moves to the next step, unfortunately that VI is no longer executing, LabVIEW cleans up the reference, and our module is left with bad references, no longer valid references. So that makes makes us unable to then communicate with our module to fire events or to hear about things that have happened. So that was a fairly big problem that needed to be overcome if we wanted to communicate with our asynchronously running modules from TestStand. We needed a way to be able to address messages to clones. So it's perfectly reasonable that if we defined a module that can communicate to, say, for example, a DC power supply that we have in our test system, it's highly likely that at some point we will have a situation where we have more than one DC power supply in our test system, and we're going to want to communicate with them independently. We might want to set different voltages or different current levels on each instance of the DC power supply. So we need to be able to clone our modules, and therefore we need a way to be able to address messages to a specific clone instance. And then finally, events and type defs are a pain to define, and they're worse, they're a pain to edit. Surely they're scriptable. This was an idea that Justin Gause proposed in his 2011 JKI private and public user events presentation at the CLA Summit. He proposed that they should be scriptable, but they are a pain to define and to create the type defs. So that kind of made it a little bit onerous on the developer to actually go down this route and create these public API methods because of the legwork involved. So some real clear benefits here, but also a couple of pain points that potentially could prevent this architecture from being a workable solution. So that brings us, without further ado, to the DQMH. DQMH stands for Delacour Queued Message Handler. What we've essentially done is we've taken that concept and we've put some scripting tools around the creation of a module. So here I'm adding a new DQMH module. This will be an asynchronously running module, in this case called Power Meter. and I'm adding it to an existing project. So this is going to be an asynchronously running module that I'm going to be able to communicate with from either LabVIEW or TestStand. I have two types of module. I have either a singleton module where I can guarantee that only a single instance will ever exist of the module. If I try to launch a new instance of that singleton module, all I will get is a reference to the original instance. We also support a clonable module where we can have multiple reentrant instances of a module running in parallel at the same time. Just to point out, DQMH Delacore Qt message handler, and it's now available on the LabVIEW tools network. So here we've added a DQMH module called Power Meter to our empty project, and the scripting code has created the module, and it's also created our API tester. So if I launch my API tester, in its template form, the module comes with a couple of methods predefined. Things like being able to show the panel, hide the panel. We also include, although this can be switched off, but we also include the ability to fire a do something else, or a do something else and wait on reply type message. And that's similar to the QMH template that ships in LabVIEW 2015 that's provided by NI. So here I've created a power supply module, and my API tester has got access to a few controls. So here we can see I've got a request event, an inbound message to my module where I can set the voltage level and the current limit, and when I change those values, you can see that the value changes on my asynchronously running module. So I've got an API tester to test those public API methods of my asynchronously running module. We have the ability to create 4 different types of DQMH event, and again we have scripting code to provide all of this functionality. This takes the legwork out of creating the user events and the type defs. We support 4 different types of events. We have request, which is an inbound message to a module requesting that it perform some activity. We have a broadcast, which is an outbound message where a module can effectively let the world know that something happened, and anybody who's registered to receive that message will receive it. We have a request and wait on reply, which is a blocking synchronous call where we make a request on a module and then wait to hear a response. And we have a non-blocking version, which we call round trip, which is a request and then a reply, but those are not synchronous activities. So I've created a new event to be able to set the power state, the output state of our module. So if you notice, the scripting code already created the type def, it created the event handling case in the top loop in our DQMH module, and it created the message case in the bottom loop of our DQMH module where I can put the actual code. It also created an empty case in our API tester, so now all I need to do is create a corresponding control on the front panel of our API tester, and then use that and the API method call that has automatically been created by the scripting code to be able to perform our new action that we've defined as part of that event. So I'm registering that case for the power state value change. I'm going to wire the new value across to the VI that you see in the center of the case. That is our public API method. Now if I run the API tester, I start the module, I show its front panel, I can now interact with my module by making calls on its public API. So I can change the current limit, let's change that value, and we can see I now have an ability to make a call to the power state public API method, and the module receives that message. The final thing I wanted to just show you is that the DQMH comes with shipping examples. If you use the NI example finder and search DQMH, you'll see that we have some fundamentals which is based around a thermal chamber. So what we're wanting to do here is give an example of how one might implement a thermal chamber controller as a DQMH module. So we've implemented public API methods such as set temperature set point, set the ramp rate, control the heater state, and monitor the current temperature. This simple VI that we're running now sets a set point of 75 degrees, a ramp rate of 10 degrees per second, and monitors that temperature by constantly reading back from the asynchronously running module. So it's fairly straightforward. In addition to that, we've also created, so we can see here, in addition to that, we've also created a device under test a device under test DQMH module that implements a power on functionality and self-test functionality. Here we're just making a call to the thermal chamber, so the same code that we saw executed from LabVIEW a second ago, where we set the temperature and the ramp rate, we're now executing the exact same public API methods, but this time we're calling them from a TestStand sequence rather from a LabVIEW VI. This is exactly the same code that we've just executed, but now being executed from TestStand to show how the public API gives us a reusable interface to our module that can be called from a variety of environments. So I'm going to go ahead and close that report. Of course, the beauty of that is by being able to call it from TestStand, we get the benefits of TestStand offering us things such as inbuilt reporting, database storage, for example. So our final example, which is the most complex of the three shipping examples, has calls public API methods of the thermal chamber and also the device under test. The device under test DQMH module is of the clonable form, so we have the ability to define multiple devices under test. In this case, we've defined 4 DUTs. So we're now using the TestStand batch model, batch process model that allows us to test 4 DUTs in parallel. So I've put in 4 different serial numbers. Now we're performing the temperature adjustment. We just have a single instance of the thermal chamber controller DQMH module performing temperature adjustment, and then now when we get to target temperature, we should perform the test on 4 instances of the device under test DQMH module. And if I move that one to one side, we can see we do indeed have 4 instances of the device under test module, each one performing its own self-test functionality. So this particular example also loops temperature, so in a way that is typical of most manufacturing tests, it performs tests at hot, cold, and ambient temperature on all 4 devices under test. So we're now performing the cold test. When we get to -25, we should then perform the self-test on our 4 modules. And in this case, we had 3 passed and 1 failed. Each one is a unique instance of that module, so even though it's only, in this case, a simulated self-test to generate a random pass or fail result, each one is its own unique instance and is capable of generating its own result. So then we've performed our final test and displaying the results, the reports of each of our 4 test sequences. So that shows how a DQMH module, and we can see here we're making the exact same calls using the public API method VIs of the DQMH module that we were making from our LabVIEW example that I showed a little earlier. So, Delacore queued message handler, what are the benefits? Well, just like the private and public events framework that I demonstrated earlier, they allow you to debug your API entirely in LabVIEW. They allow you to call that API either from LabVIEW or TestStand or both, resulting in very thin TestStand sequences. The TestStand code is merely public wrappers around API methods of an asynchronously running module. The module is responsible for performing the actual activity that you're wanting to perform. And it's a really great way of debugging your LabVIEW code entirely in the LabVIEW environment and then making the public API of that LabVIEW code available to TestStand, resulting in a lot of pre-tested and validated code before you start calling it from TestStand. The issues that we highlighted, the user event lifetime issues, in the DQMH template, we've solved the user event lifetime. The way we do this is that we make each DQMH module the owner of its own events. So when you call the launch DQMH module method, the DQMH module creates its own user events, and then returns them as part of the launch module method. Those events are returned to the caller so that the caller can register to hear about things that have happened in the module and can call the public API to request that things are performed by the module. So we've made the module the owner of its lifetime. We also needed a way to address messages to clones. Again, that's been solved in the DQMH toolkit. We've provided a numeric method of addressing a unique instance of a particular clonable module. If you launch the examples that we just showed a few seconds ago, you will see that we have in the third example multiple instances of the device under test DQMH module, and each one of those is uniquely addressed so that we can perform unique activities on a particular target instance of that clonable module. And we've put some great scripting tools around the generation of both DQMH modules and their events. It defines all of the type defs. We've put in ability to remove events if you decide that an event is no longer required, or to define new events of the different types that I mentioned earlier, the request and wait on reply, round trip and broadcast. All of that has been wrapped in some great VI scripting functionality that really does take the pain out of generating a lot of the code behind this thing. You'll see the scripting tools really are invaluable. So if you want to learn more about it, first thing to point out is DQMH Toolkit is entirely free. We want people to use it. By all means, if you find things that you don't agree with, or you want to question our rationale behind some of the decisions behind the design, or if you've got something that you'd like to add to the DQMH toolkit to make it even better, we want to hear from you. We don't want to be charging people for using this code. We want people to help us make it better. We want people to use it and be successful with it. If you want to find more about it, go to delacorp.com. We've got a products page on delacorp.com that provides links to tutorial videos. There's about 2.5 hours worth of tutorial videos on our YouTube channel. You can download the DQMH toolkit directly from delacorp.com. It is available via VI Package Manager and the LabVIEW Tools Network also, and is certified as being compatible with LabVIEW. In addition to that, I mentioned the YouTube channel. The link is on delacorp.com, and you can go and view those tutorial videos. In addition to that, we post on walkingthewires.com. That's a blog that I maintain, and both Fabiola, Lewis, and hopefully some guest presenters will be contributing to, but we often talk about user events, event frameworks, and DQMH on there. So head on over to Walking the Wires. We do try and post as frequently as our day job allows. Big shout out to Justin Goes, the inspiration behind DQMH. Before myself and Fabiola worked together, we'd both seen Justin's presentation. We'd both taken it further to solve our own unique set of problems that we had. Mine was, how do I solve the event lifetime issue, because I want to really use this thing from TestStand. That was the particular inspiration and driver behind that particular feature of the DQMH. Fabiola was particularly keen on the event scripting and taking some of the legwork out of it, and we both independently arrived at different designs that, since we started working together, we've amalgamated what we feel are the best parts of each design to give you what we feel is a great framework to use. But big shout out to Justin for giving us that original inspiration 5 years ago now. So yeah, great. And that presentation, by the way, if you Google Beyond State Machines, that presentation and some of the demo code behind it is still available. I'd certainly urge you to take a look at it, and hopefully, you'll take a look at it, you'll see the real benefits of the framework, and then realize what the DQMH toolkit can offer you in terms of some of the productivity tools that we've built into it. If you go to ni.com/LabVIEW tools and search for DQMH, you'll also get to the page on ni.com, and there's the bit.ly link for the videos. So thank you very much for watching this presentation, for giving up your time to view this material. please do have a play with the DQMH toolkit and let us know how you get on. Thank you very much.